Alright, in this example of a bar that has torsion applied to it, we've got two different materials that are bonded together. It's a coaxial torsional shaft. The inner core is a steel inner core. Its polar mode of inertia is pi over 2 in just that radius to the fourth power. It's a solid piece, so its total net polar moment of inertia is just pi over 2 inches to the fourth. The outer fully bonded piece is aluminum. It has an outer radius of 2 inches, inner radius of 1, so its polar moment of inertia is 15 pi over 2, or just 7.5 pi inches to the fourth. We're asked to find the maximum shear stress in each of the two materials, in the steel and in the aluminum. We're going to do the numbers, and then we're going to take a look a little bit about what this all sort of means. We're going to go and cut a free body diagram somewhere in the middle of this. From the side view, then, we've got our little piece like so. It's got our inner steel piece, and there's our cut location. We've got our, by right hand rule, put the fingers in the curl of the torque. That means that we would show that torque and its double-headed arrow going to the right. That turns out to be a positive torque. And then we'll show the others positive outward normal. So there's your torque in the steel, and then concentric to that will be the torque in the aluminum. Right, so that means our simple equilibrium equation then is sum the torque, state to the right positive, and so that'd be a plus 120 minus T sub A minus T sub S, set equal to 0. So therefore, in this case, the two torques add up together. Right, so statically indeterminate because we have one equation, but we have two unknowns that we have to try to solve for. So let's look at our displacement compatibility for this situation. Bill it T, there we go. And note that our rotation at B is, well, we got the fixed end at A, so that's the same thing as the rotation of B with respect to A. There's no support rotation involved. And note that with the steel and the aluminum bonded right together here at point B, that the angle of twist of the steel is also going to be equal to that rotation at B, as well as the aluminum. So in other words, they both have the exact same rotation occurring at point B. That is a direct observation that we're making here. Right, so now the next part is to say, well, we got to come up with another equation that relate these torques, and so what we can do is say the force displacement relationship. Now that's sort of notional force, notional displacement. It's really the torque angle displacement relationship, and that would be, well, phi equals TL over JG. So that means that we can state right directly off the bat here that our phi sub s, which will be our TL over JG for the steel, and we might as well go ahead and set that equal to the comparable TL over JG for the aluminum. Now note that the aluminum and the steel have exactly the same length, so those will go away, and we're left with that our aluminum torque is going to be equal to T sub A, the ratio of J aluminum over J steel times the G of the aluminum over the G of the steel. If we hadn't canceled out the L's, we could also get the reciprocal relationship between the lengths. We know those are identical, so those are already going away. And then times T of the steel. So let's get some numbers in here. We know from up above some of these ratios that exist. We've got for the aluminum 15 pi over 2, and then JS is pi over 2. We're taking the reciprocal of that. So that's kind of convenient because the pi's go away, the 2's go away, and we're just left with a 15 value right there. Then we have G of the aluminum, shear modulus there is 4,000, and that will be over 11,200 for the steel. And then we just have T sub S sitting there. So let's see what we've got. 15 times 4,000 divided by 11,200, and we get 5.357. T sub A equals 5.357 T sub S. Right? Substitute that back up into our equilibrium equation, and we'll find that our T sub S then is going to be equal to what's it going to be equal to here? Well, going to have to do the math. So add 1, we get 6.357, take the reciprocal times 120, and that's equal to 18.88 kip inches, and then TA will be equal to the balance of the 120, or 5.357 times TS, 1.101 kip inches. Right, so that is really our step 4. Math, solve for the two torques. You just did that. And then step 5 will be, let's calculate our max shear stress. That, of course, is given to us generically by tau equals T rho over J. We want the maximum, so we want to go to the maximum rho in each segment. So tau max for the aluminum then would be TC over J for the aluminum. That's our 101.12 kip inches times our outer radius, 2 inches, divided by our J sub A, 15 pi over 2 inches to the 4th. And if we do the magic, and we get 8.58 KSI. It's positive for the positive torque, and that was consistent with what was suggested as our final answer for that. And then we do the same thing for the steel, and different torque value, 18.88 kip inches times our now outer radius for the steel, which is different, that's 1 inch, divided by our pi over 2 inches. Ugh, that looks ugly. Wow, that really looks ugly. I left off the units for the torque too. So kip inch squared on the top over inch to the 4th will give us KSI. Multiply that out, and you get rounded 12.02, also positive KSI, which is what we were after. Right now, that's the basic essence. One thing I wanted to point out is if we were to plot these radially, that the steel goes from 0 at the very center to 12.02 KSI. That's your shear stress in the steel. The aluminum only gets to a maximum of 8.58 KSI. Now, if it were to be a solid, then we'd actually get different values, but from a strain standpoint, that strain would be 0 all the way back to here. So from a drawing standpoint, we could do it just like I showed that. there, and the value there would be exactly half, because that's 1 inch, that's 2 inches, so 8.58 divided by 2 is 4.29 KSI for all of those. And why I didn't do that in red, I don't know, but that's what we'd have right there for the distribution of stress. So strain is linearly proportional all the way throughout, but the stress will not, because the shear modulus changes as we go on out, and that's of course what made this indeterminate to begin with.